So, we're today learning about universal gravitation. So, I told you that gravity is pulling down on you, that there is an acceleration and that there is a force associated with gravity. If you wanted to actually calculate the force gravity exerts on an object, you'll need to know three things. You'll need to know the mass of both objects. So, for example, the mass of the moon, the mass of the earth. You'll need to know the distance between the centers. They use the letter R. So the force between the two masses, M1 and M2, are separated by a distance of R. And we get this equation. Force is equal to some constant times mass of the first object times mass of the second object divided by the distance squared. So when the masses M1 and M2 are given in kilograms and the distance R is given in meters, the force has a unit of Newton, so nothing's changed. This gravitational constant this gravitational constant, this is G, it's just a number, it's 6.67 times 10 to the negative 11, so it's a very small number, Newton meter squared per kilogram squared. But as long as your mass is in kilograms, your radius is in meters, your force is going to be in newtons. So all you really need to know is distance is in meters, masses are going to be in kilograms, forces are going to be in newtons. And we calculate between the center of one object to the center of the other object. And this is to tell you how much gravity pulls two objects together. For example, suppose that we have 1,000 kilograms and another 1,000 kilogram balls, and there's have a radius of 0.3 meters, so that when they touch, the distance between their centers as a total distance of 0.6 meters. So I'll let this one on the left be M1. That'll be 1,000 kilograms. I'll let the one on the right be M2, and that'll be 1,000 kilograms. And R is the total distance between their centers, so R would be 0.6 meters. And to figure out the total force pulling these together, that'd be F equals capital G. Note that this is a capital G, not lowercase, times lowercase m1, lowercase m2, divided by a lowercase r squared. So again, this is lowercase. This is capital, that is capital. You need to be using the same notation I use. If you use lowercase g, that's another variable entirely. So G is equal to 6.67 times 10 to the negative 11. And then I'm going to multiply it by the first mass, 1,000 kilograms. Multiply it by the second mass, 1,000 kilograms. And then you can divide the whole thing by the radius squared, so 0.6 squared. Note that you can pull this g up to the numerator so that it's g m1 m2 over r squared. These two equations are the same thing. No, you don't. Because there's only one thing in the parentheses. I just usually do. I usually put things in parentheses, but you don't really have to. I would highly recommend anytime you use scientific notation, so times 10 to the whatever, you put this in parentheses. So multiplying this out, you get an answer of 1.8527 repeating times 10 to the negative 4. And this would be force, so force is measured in newtons. Note that your calculator uses this symbol E. This E means times 10 to the negative 4. You could also use E to type it in. You should see it on your calculator. I don't know where on y'all's calculator. On this one, it's in blue. Here it says double E. So you can press second. So let me put, like, for example, if I put 5 second E2, it's 500. That's the same thing as 5 times 10 squared. They're both equal. So these notations are the same thing. I don't know where the double E is located on your screen, your calculators. But if you're using Google as your calculator, you could still do that. You can type in 5E2 and Google will recognize the E meaning times 10 to the square. And E means times 10 raised to the whatever number comes after. And when reading off the calculator, you replace the E with a times 10. So again, on the calculator, it gave me E negative 4. So I replaced the E with times 10. And what number comes later, I put that up as a superscript. So I'm really not meaning this to be a cross. So in physics, we use x's. In scientific notation, when you write a number like this, I recommend you put an x. But you notice I didn't use an x or a dot here. I used parentheses to represent multiplication. You'll see that in physics, we do not use x when working it out, except for in scientific notation. We represent multiplication by parentheses. So here, there's no confusion. Anytime you see this cross symbol, it means times 10. And multiplication is signified by using parentheses. That removes the error whenever you're doing your work. In algebra class, when you first learn algebra, I highly recommend you use dots. But usually, scientific notation is always written using a cross, or what looks like an X. You can this just looks weird because you never see scientific notation written with a dot. This is just a way of writing a number. And it's not really an X, it's more of a, can't even draw it. It's more like a slanted cross. So here you can see that they did the same thing. So they wrote it fully out with the units. Note here that they did the distances, and yes, here you would have to use parentheses to do the square because they didn't add it together initially. and they get 0.000185, which is the same thing as 1.85 times 10 to the negative 4 newtons. This is standard notation. This is scientific notation. So this is a very small force. Do you know how much a newton of force is? So to give you an idea of how much force 1 newton is, take an apple, an ordinary apple, grab it, and lift it up 1 meter in 1 second. That requires exactly 1 newton of force. That's actually how a newton was initially described as. Isaac Newton did it, and he's associated with apples. But you take about the weight or about the mass of an apple, you raise it up 1 meter in 1 second, and that is 1 newton of force. So 0.000185 newtons is a very, very, very small force. That is why if you put 2 cars next to each other, they don't push together due to gravity. They're pulling on each. Gravity is causing them to pull together, but they can't overcome static friction. Remember, in order to get something started to moving, you have to overcome the static friction. Otherwise, they just stay still. But 2 cars in a parking lot will be pulled together by gravity if it wasn't for friction. So if 2 spheres were touching each other, the gravitational force between them would only be 0.000185 newtons. On Earth, this corresponds to a weight of mass equal to about 18.9 milligrams. So, giving you an idea, let me type it in. 18.9 milligrams in pounds. So that is a very small number. It is 0.00004 pounds of force. So way less than a feather. So imagine putting a feather on a car and expecting to move it. It's not very strong. So let's work out some examples. So calculate the force between 2 objects having masses of 70 kilograms and 2,000 kilograms separated by a distance of 1 meter. It doesn't matter which one's M1 and which one's M2. So I'm going to let M1 be the first mass of 70 kilograms. And I'll let M2 be the second mass of 2,000 kilograms. Capital G is always 6.67 times 10 to the negative 11. And it's newtons by meter square, kilogram square. And it says that a distance of 1 meter. So we use R to represent distance. The reason we use R is because R stands for radius. And if you were to imagine the radius of a sphere, this is the radius. This is also the distance from the center to the surface. Or if we look at the moon, we can draw a circle around the Earth, and it'll be the radius of that circle. That's the reason why R is used. So F equals, the force will be equal to G, M1, M2 divided by R squared. So we plug into the calculator 6.67 times 10 to the 11 times M1 is 70 kilograms, M2 is 2,000 kilograms, and or R, we would divide by R, which is 1 squared. And we get a very small force of 9.338 times 10 to the negative 6. This is force or unit newtons. This is also equal to so 1, 2, 3, 4, 5, 6. So this number is the same thing as this. Has a very, very small number. Everyone good? What? Yes. The video will be posted online. So calculate the force between two touching grapefruits with a radius of 0.08 meters. It might be better to do a picture. So we have two grapefruits. The radius is 0.08 meters. And then we have another grapefruit whose radius is also 0.08 meters. So the distance between these two dots would be twice this amount. So the distance between here and here is 0.16 meters. So our R value is 0.16 meters. Our M1 and M2 values are both 0.45 kilograms. And G is a constant. So when solving it, F equals G M1 M2 divided by R squared. That would just equal 6.67 times 10 to the negative 11. Yeah. Zero point 0.45, 0.45, all that divided by the radius, 0.16 squared. I recommend you try typing these in the calculator to make sure you understand how to type it in. Make sure you're able to get the same number I'm getting. So this would be equal to 5.276 times 10 to the negative 10. And this is newtons. So here we're now going to figure out the force between a grapefruit sitting on Earth's surface. This is equivalent of finding out what the weight of the grapefruit is, because the force due to gravity is the same thing as weight. So this is not to scale. We have Earth. Earth has a radius of 6.3710 times 10 to the 6 meters. And then we have a grapefruit that has a radius of 0.08 meters. Earth's mass, I'll let Earth's mass be M1. M1 would be 5.9742 times 10 to the 24 kilograms. Earth is very massive. I'll let the grapefruit's mass, which is 0.45 kilograms, be M2. Which one? Yes, this is 3. So we can write F equals G M1 M2 divided by R squared. So our G is always 6.67 times 10 to the negative 11. Or mass 1 is the mass of the Earth, 5.9742 times 10 to the 24. Our M2 is 0.45 kilograms divided by the distance between the two centers. So here I would have to use parentheses and go add these numbers together. 6.3710 times 10 to the 6 plus 0.08 close parentheses squared. No, you can draw it any way you want. And I get a force or weight of 4.41915 newtons. So how I typed it in, I did 6.67 E negative 11. And then I did times 5.9742 E24. Then I did times 0.45. And then I did divided. I used parentheses. 6.37. That should be a 1, not a 0. Plus 0.08. Put a square up top. Press enter. And my answer is going to change because I made a mistake. That should be 4.4177 newtons. Seems simple enough. All you do is just take and identify your variables and plug it into the equation. Everyone good? So let's do 4. A man on the moon has a mass of 90 kilograms and weighs 146 newtons. The radius of the moon is 1.74 times 10 to the 6 meters. Find the mass of the moon. So I'm going to let the man be M1. So M1 equals 90 kilograms. The force due to gravity. So F is 146 newtons. And we have the radius is equal to 1.74 times 10 to the 6 meters. And it asks you to find the mass of the moon. So we have this equation, F equals G M1 M2 divided by R squared, and it's asking you to solve for M2. This requires algebra, and I know not everyone has algebra, and there's no way to set this up using a triangle, so I will just solve it and tell you what it is. So M2 would be equal to force times the radius squared divided by G times M1. Do note that if you have two terms being multiplied on the denominator, you should put them in parentheses. So this is the equation for solving for one of the masses. Again, it doesn't matter what your M1 or M2 was. You can always switch them around. So our force would be equal to 146 newtons. We times it by 1.74 times 10 to the 6. And we square it. So this is your force, this is your R squared. And then we need to divide it by 6.67 times 10 to the negative 11. And then multiply that by your M1. Our M1 was 90 kilograms. Don't have to put units really when doing it. Make sure when typing in the calculator, though, you put the entire denominator in parentheses. If you don't, it will come out with the wrong answer. Always put your denominators in parentheses so that it multiplies this together in the denominator first. So typing it in, that'll be 146 times 1 point, and I'll put this in parentheses, 1.74 E6 close parentheses squared. Then divide, and I need to put the entire denominator in parentheses, 6.67 E negative 11. Make sure I typed everything in right, yes. And then times 90, close parentheses, and we get 7.3635 times 10 to the 22, and this is mass, so we use kilograms. So you can figure out the mass of an entire planet just by knowing its radius, how much an object on the surface weighs, how much you weigh, and how much mass you have. So if you knew the radius of a planet, you can take an object and weigh its mass and its weight in newtons, and you can calculate the entire mass of the planet. And it's all given in this equation. Everyone good? So for remote learners, that's the code word. Code word is this. It's 2 words. Yes, you've already accepted it. So what is the original equation for force? So F equals ma. This is our main equation for force. I just gave you another equation. F equals G m1 m2 divided by r squared. If I look at this portion of it, and I rewrite this so that we have G times m2 divided by r squared, and I times it, or let me write that differently. So if I take and pull this out, so that F is equal to m1 times G m2 divided by r squared. Now look at it and compare it to F equals ma. We have some mass times something else. So some mass times something else. What do you think this is going to be equal to? Acceleration. So you can find what the acceleration of gravity by using the constant g times the mass of the planet divided by the radius of the planet. So this would be acceleration of gravity. We usually let acceleration due to gravity be equal to lowercase g. So acceleration due to gravity is equal to this constant g times mass of planet, and this will be the radius of planet squared. So let's look at problem 5. I think that's mass of the Earth. Yeah, so this is the mass of the Earth. So mass of Earth is equal to 5.9742 times 10 to the 24 kilograms. The radius of the Earth is equal to 6.378 times 10 to the 6 meters. And if we solve for this, G times m divided by r squared. This can be also written as G m divided by r squared. So we plug that in, 6.67 times 10 to the negative 11 times mass, 5.9742 times 10 to the 24. And we divide it by the radius squared. Again, if you're typing this in, it's not done in notation, do make sure you include parentheses before you square it. We get a value of 9.7957, and the units for this part is going to be meters per second squared. This can round to 9.8 meters per second squared. This is the acceleration of gravity on Earth. And I've been rounding it for you guys to just 10 to make the calculation easier to do on homework. So, given Earth's mass and its radius, we can calculate the acceleration due to gravity. Note that this would be the value of gravity on Earth's ocean. If you were to go up to Mount Everest, you would be farther away from the center of the Earth, so gravity would decrease. It won't decrease by much. Like a millimeter per second less. There's another differences too. Have y'all ever looked at diagrams of Earth's what it's made of? You have a core, you have a liquid core, the mantle, and crust. Technically, Earth is not uniformly dense, meaning that it has pockets of more mass. So you can have like a lot of iron right here, and if you're standing under it, it'll pull down closer, pull down more to you. You're closer to a bigger mass. We get values that more range between 9.8 and 9.81. We can get values less than 9.8, closer to the true theoretical value. I'll do one more example and then we'll be it for the day. So the distance between Earth and its moon, the centers of it, the distance is 3.84 times 10 to the 8 meters. Earth's mass, I'll let Earth's mass be M1. That's 5.9742 times 10 to the 24 kilograms. And the mass of the moon is equal to 7.36 times 10 to the 22. You can notice that on the previous example where we calculated the mass of the moon, you can see the mass of the moon is right. And ask, what is the force between Earth and the moon? How much force is the moon exerted on the moon to keep it going in orbit? How much is the Earth pulling on the moon? So we can calculate that force. So it would be equal to 6.67 times 10 to the negative 11. M1, actually I'm going to write this down below. So M1 is 5.9742 times 10 to the 24. Mass 2 is 7.36 times 10 to the 22, all divided by 3.84 times 10 to the 8, and then we square that. And we get a value of, let me make sure, a really large number. I typed this on the right. Yeah, that's right. 1.9889 times 10 to the 20 newtons. So that'd be 19889 So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 newtons. $15. That is a lot of force. This also corresponds to the weight because of the moon. The moon weighs a lot because it has a lot of mass, and it's inside of Earth's orbit. Let me ask you this question. Which weight is bigger? Earth, only looking at the moon and the Earth. Earth's weight or the moon's weight? Ignoring the sun. So let me ask you this: which pulls more strongly? So we have the Earth and we have the moon. The Earth pulls on the moon, and the moon pulls on the Earth. Which one of these are bigger? So remember that I said you can swap the masses around. It doesn't matter which one's M1 and M2. So we calculate the force the moon exerts on the Earth. It'd be the same thing. They both pull on each other with the same force.